Good. Now it will become a little bit, how do I organize myself? It will become a little bit improvised. Yeah. So we are not going for slides now, but let's apply at least with one first example. Let's apply it to real, let's make a real data analysis with texture and microstructure. And later on I can also speak a little bit about EBSD as a technique in general, yeah. But now we will use a little bit texture analysis with the OIM software to look what we can do with it, yeah, and how we handle it. And that means, however, that I need somehow a proper place where I can see these guys and my computer. Maybe I'm sitting on the back side of this thing here. Right, I think that will do it well here. Yeah, that's perfect. I think this is just fantastic. Okay. Yeah, good.
But I need to go out.
Oh yeah, you go out. I will manage myself. If the student
from here.
From here. I see. Okay, good.
Not completely.
Okay, I see. Right. I wanted to say you can go out. I have my stick for the students. Good. So let's see how we start. Where is the example? I have still example. Yes, that is the one. Mm-hmm. Exactly. So also I need the software dongle. So the aim is now not really to teach you in using the software, but you will of course see that as well. You will see a few tricks, I believe, but rather in using EBSD data for texture analysis. Yeah, and I have one interesting subject. So actually, maybe one question to you: who is there someone between you who is working really on textures? You are. Oh, there's a few people. Ah, yeah. All right. Good. But everyone is working with EBSD. Actually, everyone has touched EBSD already. Not everyone, but okay. So what you will see now as an example is a sample of an interstitial free steel, which is used for deep drawing applications. And that means you create it in sheet form. And then you use this, for example, to make cans out of it and so on. And for these materials, texture plays an important role. As if the texture is not correct, you will get earring during deep drawing process. You will get different thickness in different directions after deep drawing. So that's a big problem. And the question is, do we get the right texture? And of course, for me, the question is more not this technological question, but do we understand how these textures form? That was one of the questions, and I have one example on that one. No, not like that. Do I have 6 or 7? Is it here? No, that's 7. Yeah, that's what I thought. Right. Good. Open the software. And then close this one here. And for other width, keep this up here. And missed it. Sorry, I should have used the break to get myself prepared. So let's hope it works. Oh yeah, there's already plenty of stuff. All data. And let's look just on this one here. Just to make sure that this is, this is exactly the data set I wanted to see. Exactly. Oops. All right. So what we see here is a material which has been cold rolled and then partially recrystallized, and we want to and this is, as I said, an IF steel. For texture analysis, the area would be a little bit small, particularly the recrystallization area, because you can count still by hand 1, 2, all the big grains which are more or less globular, spherical, are the ones which have been recrystallized. And this is roughly 100 perhaps, yeah? So it's probably a question, and we will see later on, whether this would be sufficient as a sample for texture representation. Good. And the first thing now is to make sure that we have measured the thing in the right direction, that the orientation, that the sample coordinate system has been selected correctly. And honestly saying, I'm not quite sure whether these data have been rotated already. So maybe I quickly have a look into the discrete texture plot. Stop it. Because then I can explain you something with respect to that, which I would like to do first. But I just need to see whether it's correct or not. Oh, there it's written. It's already rotated. Yeah. Okay, then it is already done correctly. Okay, but then I will not explain it live here, but I will shortly draw something. You may be all aware of it, but I know from my students that even if you're aware, you're still making mistakes. And even I need to give it a second thought. So, yeah, this is already correct. This shows that all the things which I wanted to show you have happened already. But let's have this disappearing again and just showing this picture here. Good. So, you see the grains are elongated in this direction. That means the sample has not been measured by looking on the rolling plane, but by looking on the rolling direction, in the rolling direction, yeah? So, if we had this material being rolled, up, again my stupid same, this is the rolling direction, and this material has been either measured on that side here or on that side here. I don't remember perfectly, but it doesn't matter. Let's just assume it was on this side here. And we measured an area, something like that here. Yeah, so this was our measurement area. Why do I select a cross section and not, it would be much simpler, it was a thin sheet, would be much simpler to look on that sample surface here, yeah? Then you just polish the sheet, you don't need to have a cross section, you don't need to mount it properly, everything easier. But if you look on that surface here, you will see something very special when you have this rolled material. You will see grains which have no clear borders, and sometimes you have another grain coming up, and then another grain coming up again. You will not see proper grains, usually, in a deformed structure, and the reason for that is that these grains, when they roll, they get kind of wavy grains, yeah? So they are not any longer nicely shaped, and so if you make a cut here, you will see the same grain several times here, and so when you make a horizontal cut through it, and this grain will dive below the surface, and then there will be a bit of another grain, and a grain coming up again. So the normal observation of such structures is the most inconvenient observation you can make. No? So therefore, it is usually best is to go to this or to this section here. This one when you want to measure textures, because you get the biggest amount of grains on a smallest surface. And this one if you want to see, for example, whether there are shear bands going through. No? That's best to see here. You can't see it on this surface here. So this is a consideration. But okay, now we have made a proper decision. We measured on that thing here, and we placed our sample like that into the microscope. The electron beam came here, and our grains are here. So, okay, and now the software makes an assumption for you, which you are probably all aware, to think that you have put your sample into the microscope with this direction being X, and the normal direction of that sample, out of that sample here, so out of the board, being Z. This is the usual convention taken in the OIM software. If you are measuring with Oxford, then they assume actually that this one here is X and Z is out. Yeah? And of course, you can always select in the software and you say, this is not X, I will call this A. No, you can say this will be Y or so. No? You can select it, but by standard, by default, this is the selection. And let me remove this one here again, because this is not the right one. So, but of course, texture traditionally has a different setup, particularly when you're talking about rolling. Yeah? Then actually, the people would expect that you describe the texture with respect to this surface here. So you would say, this is my normal direction, and this is my rolling direction. So we call this X, X, and that, and here is Y. Now this is different, yeah? So we have called this one here X, which is perpendicular to the previous rolling direction. So you will see a microstructure nicely, no problem, but your reference system is different from the traditional reference system taken usually for a rolled material. Yeah? You could also think that this is a sputtered material, something like that, and you are looking on the cross section in order to see the columnar growth of sputtering. Then also you will not have the proper setup of your sample orientation. So if you want now to have the texture representing like it is best selected, you need to take that texture as you measure it here, and you need to rotate that texture in order to represent to that one. So you see here, how do I get from that setup to that setup? I just need to rotate 90 degrees. How can I display 90 degree here around the Y direction? Then this X will correspond to this X. So when I have measured my texture, the first thing I will do is a rotation of 90 degree around the Y direction. 90 degree around Y, so about that axis here. Then all the texture data will now be corresponding to the standard setup which you would select for a rolled material. You're not changing the direction of observation, so you're not, whoops, switched off. You're not changing, of course, the observation direction. You're still looking on that sample, but your color coding will be different. The colors will change, but of course everything else, the shape of the crystals and so on, will still stay the same. And of course now, if you have done that, and you want now to measure, okay, so the colors are corresponding now to a coordinate system standing like that, no longer standing like that. The software doesn't know that internally, yeah? You have done it, you have done this 90 degree rotation. You must keep it in mind, okay, this is all rotated. That means when I now show a crystal, so I can do that with the software. I can go to lattice and plot here this crystal, for example, yeah? This crystal orientation for this particular grain will now correspond to the situation that I look from here on that crystal. No longer as I have measured, looking from here. No, the microscope was looking from this direction, and the crystal would have been 90 degree rotated. Now we have done this rotation here, in this case actually 90 degree around TD. Yeah, this is exactly what I showed there, so I was obviously right. And that means when I display this crystal now, it would be as if I would have looked from that direction. Of course, I have looked from the front, but all the orientation data have been rotated. It's a little bit complicated to remember, and that means also when I now want to measure, for example, okay, this boundary here, to which plane does this correspond? Can I see that? Where is it? Oh, this is close to 111 here. No? Wrong, because it has been rotated, this thing here. No? There's no longer this view here. So if I want to make this boundary, where is it? Then I need to rotate back and must come to the original orientation where I see this picture like I see the crystals. And that creates really confusion. Huh? People start now you can do this with the software also. You can plot, let me see, this one here, for example, you can plot this little crystal in here. How is it done? A shift. No, that's not what I want. Here. No, not either. 1, 1, 1, 1. That's not what I want. I have to remember how to do it. Clean up. This should be right. And I need this one here. I think I need this one. No, that's not the one. No, this should be right here. Give me a moment. I think it was like that. Which orientation? No, that's also not it. Maybe I have to go and say show highlighting. Oh yes, oh yeah, and then it's miniature. You see now a miniature crystal in there. Let's shortly zoom in here. Okay. But it's probably not bigger. Yeah, where is it? Because I cleaned up. All right, then let's click there again. Okay. Click here. Yes, okay, and now I need to make it a bit bigger. Highlighted boundaries. Okay, let's make 20. Okay. Yes, okay, good. So now I have plotted a little crystal inside, and you would now look, once again, you could now say, okay, this crystal stands like that in the sample. No, it's not right, because the data are all rotated. The crystal stands like that in the sample if I would look from top here. No? But I look from here, so in principle, this is not the right plot. Okay, I hope that is approximately clear. There is some trouble with that, but for our texture analysis, it's better to rotate such that we are in a standard orientation. And you will see why. So of course, the drawing of this crystal is right, but you must remember, it is like I would observe it from the top. It is no longer related to the morphological data of this grain here. From the top, the grain would look different, no? But I haven't taken that cut. So let me remove that again. Okay, and let's go back to standard size. And let's also show for a moment no boundaries. It looks a bit more beautiful for the beginning. All right, good, good. So now we want, sorry, one more thing. Show boundaries was good, but I showed too many small grain boundaries. We need to speak about grain boundaries later and about misorientations. Almost very important, but not for this one here yet. But before I'm going to my teaching in the afternoon, I will make a short teaching also about misorientations, and then we can go for another example. But here, let me shortly look for the properties. Let me take off the low angle grain boundaries, and then it looks a bit more clean. Yes, okay, that's better. So now let's look on the texture of this material, and take off this one here. So it's already clear what the colors means when this is red. It's an 001 orientation, but it's an 001 orientation by looking from the top here, no? And this is a 111 orientation, but with respect to looking from the top. So let's try that shortly. I will plot the crystal and point into this grain, and then we should see the 111 plane, the 111 tip of the grain pointing upwards. Let's hope that this is correct. Yeah. Let's hope that I'm not confusing myself. Now it's, what am I showing here? Okay. I was not correct. Okay. And why not? Because the coloring the coloring which I have taken here is, so I have rotated the data, but the coloring is rotating it, so to say, back. The coloring shows really what kind of crystal orientation points out here. Yeah? So that should be somewhere written in the legend. Now I'm well able to confuse you. It's, yes, let me see. 001. Even I am confused now a little bit. Is it really like that? Lattice. Yeah, it's clear. Yeah, you see when I'm touching a red grain, I'm always seeing the plane, yeah, the 001 plane. When I'm touching a blue grain, I'm always looking on the corner of that grain. So, and unfortunately there is no green grain, which we could try, but red and blue is there, so that's very clear. That means in colors, I'm showing the orientation which points out here. And why is it 001? It is rotated, that's for certain. Okay, yes, it is rotated. That means this is this 001 means normal direction. Yeah, of course. Yes, I'm confusing myself. That's the point. And it's exactly this confusion which I promised you to happen. I have rotated the data such that something which actually points up is pointing up there. Yeah? So the normal direction is now no longer this one, which I have measured, but it is this one, which I have not measured. So when I'm plotting the normal direction in colors, and that's what I'm doing here, I'm plotting the inverse pole figure for this sample direction. For the 001 sample direction, this is the z direction, x, y, z. So, and the z direction is usually the normal direction pointing out of the sample. So that's what I did. I rotated the data such that this will be, that the normal direction is oriented like that. And at the same time, I'm plotting now this direction. So I'm plotting this pointing out direction in colors. And that means if I click on one grain here, and this grain is actually pointing with 111 in this direction, it will look here as if it points towards us. Yeah? The color indicates that, is good. And the orientation, this grain which I have plotted here, also indicates it. But the grain is not pointing towards us. Yeah? It has been rotated, it points towards up. And even I can get confused sometimes. Yeah? So be careful with this. No? So I have selected the right color code for the fact that I would look from the top. And that is all consistent. That means these grains here, these blue grains, all have their 111 directions in the direction of the normal, and the red ones have their 111 directions in the direction of the normals. That means, if I plot that again, so a grain which appears here, so in red, on that surface here appears in red, it means that the grain has somehow its normal direction in this plane here. So this one here, ND, is parallel to 001. Then it appears in red here. Yeah? And if it's a bit more difficult to draw, if it is having something like that, yes. If it has this one direction here, ND parallel to 111, so the 111 points up, then this grain here will be drawn in blue. So that's it. No? We are looking in this direction, although it seems that when we plot this crystal, it points out. But in reality, it does not. Yeah? All right? Good. I say good. I don't know whether you agreed with all right. Yeah? I assume it now. Okay, so we have now done this first start. Now let's look on the texture distribution. And I have plotted here already the pole figure. Let me go only for one pole figure. Properties. We'll take only this one, yeah, exactly. Remove that, and plot that one, okay. So now let me plot this pole figure. So what I'm plotting now, yeah, that's very nice to see. I'm plotting now all the orientations. If I look from here, where are all the 1, 1, 1 planes? As if I would looking from here, so the ND direction is here in the center, and X is down here, and Y is down there, is horizontal. And what I am seeing here now, of course, is a bit difficult. If you would look on my computer, the resolution seems to be a little bit better. You see that there is some intense pole here. But shows already, you cannot say, is this one here more intense than this one here? It's just black. No? Black, or a little bit black. No? But it's all black. So this shows already we need texture analysis to know is this pole more intense than this one or not. No? We need to calculate the density distribution function. But you will see actually that this pole here is very, very high. That means lots of 1, 1, 1 planes are pointing out here. And this was in ND direction. So lots of 1, 1, 1 planes looking in ND direction. Wrong button. Where was it? Yep, this one here. 1, 1, 1 planes in ND direction. This can only be the blue grains because blue is 1, 1, 1 in ND. No? And you see actually here's lots of blue in this microstructure. Lots of blue, that means obviously, let's put these things next to each other. All these blue grains here must correspond to at least one pole here, yeah? Or this one here as well. And this one here is a little bit purple. This will be a little bit off from this pole here, but in principle. And the red ones, all the red ones, they will be not visible here. Well, they are somewhere, but I don't know where they are. But red I know is 001 parallel to ND. So let's plot also the 001 pole figures. So we go properties and we say add 001. Okay, 001 here, yeah. And I say okay. Now I will plot. I hope they appear next to each other. Unfortunately, then they are quite small. Can't I make them top of each other? No, it doesn't matter. Huh? Why is it not doing it? Oh yeah, there it's coming. Okay. Okay, let's make. I need a bigger screen to have everything properly displayed here. Let me see. Layout. Okay, that's possible to do, of course. Yes, okay. That's better. So, the Teacher's Memorial Minute. Okay, there we go. So, 1, 1, 1 poles. Is this okay for you that I'm teaching like that? Is it interesting for you, or do you think it's totally boring? Is it okay? Yeah, you learn something from it, or it's all familiar with it? No, okay, good. So 1, 1, 1 poles were all the blue grains, and now all the red grains should be also in the center. So there should be also a pole here in the center, in the 001s, which corresponds to all these red grains. Okay, now we make the test whether the professor is right or not. Yeah, I'm a little bit worrying that I'm not. Let's hope it comes out right. I will mark one of the blue grains in the right map and hope that it turns up to be visible here, that it will mark these points here. Yeah. So I will say show highlighting, and then here I will also say show highlight. Oh, this is already on. Okay. And then I will select here better to select to color one grain. Okay, maps grain coloring. And I will go into one grain which looks nicely blue. This one here, for example, at least on my computer, it looks more bluish than there. I will click into that. And the software is now coloring that, and it should color it also here, and it does actually, but it's not so well visible. And it's also not so well visible because the color coding here is not so fantastic. I think I need this one, yes. Blue, should we take blue? In order to see it better, I don't take blue, I take yellow, reverse, okay. And I click again on this grain, yellow is also there. Green, let's take green. Green we don't have anywhere. So green, we take this one here, reverse, okay. And I click on that grain here, and it will color this grain in green. And we should see this grain turning up here to give a point here. And indeed it does, yeah, it's a bit too many points, but I hope you can see that there is now a little green dot appearing here in the center. Yeah, that's exactly this 111 plane pointing exactly in the middle. Now you know 111 planes are 4. There are always 4 111 planes. That means if there's one here, there must be 3 others. And actually this is this, and this. So this grain stands with its 4 corners. It's a bit difficult for me to show. We just look on it again with this crystal drawing here. Blah, blah, blah. No, how do I get there? Here. Lattice. Yes. No. So we are seeing one pointing out and 3 other corners, 1, 2, 3, pointing to the sides. And of course, it will appear also in this one. Of course, it will also have an 001 direction. Yeah, this is clear. It has also the cube corners, and they are here. No? 1, 2, 3. Okay, that's 3 in 001. Three surfaces and 4 corners pointing towards us. All right. Now let's take a red one, and the red one I can promise already will appear somewhere here in the middle. And the others I don't know now with details, but let's look on that. Let's take a nice red one, this here for example, and I need another color coding to separate that. Okay, this time I go for yellow. Reverse, okay. Click into that one here, click. It will search all points belonging to that grain, and indeed, whoop, I was right. You see, this is coloring here quite in the center, so the 001 direction is pointing. It's not pointing out, it's pointing up, no? Because we have rotated the data. But okay, if we consider that, then everything is good. And actually, the other 01s, this is quite an interesting grain. It's really standing under 45 degree. That means it's exactly fulfilling here at 45 degree these corners here. And so it's a very highly symmetric orientation which we have here. No? These are 4 111 corners and the 3 100 corners. All right. And what you also see, the green was just one single point, yeah, or a few points only, because this is a recrystallized grain, and the yellow is a deformed grain, and that's why it has quite a spread of orientations. That's why we are seeing it better. Huh? It's more orientations covering in space. Oh, and that shows already, obviously recrystallized has always a peak here, and recovered has always, and deformed has always, almost always a peak here. Actually, there's 2 sorts of deformed grains, the blue deformed grains and the red deformed grains, and there's more or less one sort of recrystallized grains, and that is only the blue ones. And now you can say, hey, why only the blue ones form out of a texture which consists of blue and red? No? And that's actually one of the big questions. How do these textures form? And you see already one interesting thing. Now we learn a bit about material science again. When you look into the deformed structures, and we will later on find out how we look into that, you see the blue ones, you can see some substructure. Yeah, you see pink, blue, pink, blue, pink, blue. There seems to be some substructure inside. While when you look in the red one, you don't see this clear substructure. It starts yellowish, then it turns red, 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 but there is no separation inside. Yeah? In the red grains, there is a homogeneous orientation gradient, while in the blue grains, it seems to be discrete. You seem to have recovery. There seems to be some some sort of recovery going on. Here it's as well very clear, yeah? Well, this red grain or this one here has quite a homogeneous structure. And this is actually the reason the blue grains, which are 1-1-1 oriented grains, they have a dislocation structure which is rather mobile. So when you do this rolling here, then these dislocations can arrange and can form subgrain structures. The red grains have dislocation structures which are entangling each other and which are not very mobile. And therefore the red grains stay in their continuous orientation gradient. And this will later lead to the fact that this one can nucleate. It nucleates new grains, while the red grains do not nucleate new grains. Yeah? And this is already visible a little bit in this structure, yeah? But we want to see a little bit more. We want to separate now deformed structures from recrystallized structures. So and then, of course, we want to see the texture. Maybe we can already look on the... Now we will do the texture looking, we will do later. So yeah, I could, of course, go and plot the blue grain behavior here once. Come disappear. So I click on one of these blue grains, I give it still another color. Wait, here. And now we are running out of colors. Usually I like very much pink. I'm such a pinky person. Okay, let's take this pink. I don't like it so much, but it is a kind of a special color. Now we do have that as well there. And let's go for a real pink. No, this is also too not very clear. But okay, let's keep with this. And let's go for this plotting here. Somewhere here. Coloring it. Yes. Okay, and again, it appears well here in the middle, yeah? Overlaying with the green grain, that's why we don't see the green one any longer. And it has its peaks here. In contrast to the green one, which has really just one point, it is spread out. And you will see, actually, there is a 30-degree rotation between the green and the pink. Green and pink, 30 degree. Green and pink, 30 degree, all rotating around that. And actually, this is one of the keys of recrystallization here, that there is a 30-degree rotation between the deformed structure and the recrystallized structure. And this 30-degree rotation is probably because there is special grain boundaries in between the deformed crystals and the non-deformed and the growing crystals. Yeah. So we see this already here, but of course we need more considerations to figure it really out in details. Well, in order to do that now and to do a bit more statistics, we need really to understand which one of these grains is recrystallized and which ones are deformed. Now for that, let's make a trick. First I clean up here clean up everything. Okay, and what I will do now is I know deformed grains have an orientation gradient inside. Non-deformed grains have no orientation gradient. They are homogeneous. They have only one orientation. So I can probably use this information. I can see it already. Now all the recrystallized grains are homogeneous in color, while the deformed grains are not. So I can probably use this information to separate deformed and non-deformed grains. So let's try that. And I will plot a measure for deformation. Now I need to open that here again. Okay, this grain, I will plot a new map. And this map, let me think which measure I will take. There is some measures for kernel average grain orientation spread is, I think, quite good. The grain orientation spread indicates how much is the maximum change of orientation inside of one grain. Yeah, so if I plot this value here, grain orientation spread, this would show me what is the maximum difference in orientation between the smallest and the largest orientation, if you want. Yeah, so that would probably be a good measure to separate between the recrystallized and non-recrystallized materials, because the grain orientation spread in the recrystallized grains should be very small, and in the others it should not be so small. So let's plot that, and What did I want to say for that? Oh yes, one thing you need to know for that is, what does the software consider to be a grain? Yeah, so if I say grain orientation spread, that means the software first must have an idea what is a grain. And you need to define that. There is a default in the software, but before you're getting lost, you should check on these defaults. Yeah? And so let's do something different before. Let's first, no, not this one. Let's first make a plot which shows us crystals, unique grain color. So unique grain color will show me, why is it not eddy? Oh yeah, no, that's correct. So let me plot that, unique grain color. Unfortunately, we need a bigger screen in principle to show all these things next to each other. But okay, I don't have it. So what it's showing here now is every grain has a different color from its neighbors. Yeah? So similar colors mean nothing in similarity. That just means this grain is one unit and its neighbor has a different color. There is actually a special algorithm behind which makes sure that there is never same colors of different grains coming next to each other. So a yellow grain will not have a yellow neighbor. So that's a beautiful algorithm. We can also now plot again grain boundaries inside. I should do that. So properties, add large angle grain boundaries in black. Okay. And you will see now that all the grains have a large angle grain boundary, and you will not find an instance where two grains with large angle grain boundary have the same color directly touching. So this is a helpful thing to see what the software considers to be a grain. For example, this whole thing here is one grain. This whole thing is one grain, and you could ask the question, is this properly separated? No? There is a little funny green thing in here. Seems to be a new grain. And I just want to plot again these things next to each other. And we close that for a moment. No, we don't need. Once again, next. So where was that? This little green grain. Yeah, that's interesting. Good. Look here. There's a little green area. That means the software considers this to be a new grain, yeah, a separate grain. While here, in this picture here, it doesn't look like a new grain, yeah. And also, this green grain doesn't have a grain boundary all around. On one side, it has obviously. I plotted grain boundaries larger than 15-degree misorientation, but this grain obviously has only on one side 15-degree, on the other side not. So why is it considered to be a new grain? And something similar we'll probably find somewhere else. Let me look whether I see. Yeah, for example, interesting here. This grain here, this one, and this one here. It seems to be actually not one grain. Yeah, so this one is actually looking clearly, this is a new grain, and this one is a deformed structure. I would guess this grain has grown out of this deformed structure. That's why they don't have a large angle misorientation here, and they grow into. But the software has considered this to be one grain. Also not ideal. So in this case we can maybe tolerate that, but you may have situations where you don't want to tolerate that. I see that frequently. So how can I control what the software considers to be a grain? For that you need to, the best would be I go to a new, for this you go to this thing which is called let me see. How do you call it? New partition, of course, meine Güte. Sometimes, so you go to the partition and you say the properties of this partition. So partition means a certain selection of pixels out of the original full data set. One full data set, one partition could mean all data, could be called all data, means it contains, actually it has no partition restriction, but you could also say I want to see a certain restriction. And in this partition you have properties, and one thing is called grain size. And you can look on this partition and you see here a grain is considered to be the following. It must have at least 2 pixels So if it's only an individual pixel, it's not considered to be a grain. You could say, oh, even if it's only 5 pixels, I don't want to call it a grain yet. It's still a wrong measurement or whatever. You can change that, yeah? And it must have at least a misorientation of 5 degrees to its, this pixel must have at least a misorientation of 5 degrees. You could say 5 degrees is for me not small enough, not big enough. No? I want a grain only to be called a grain when it's at least 10 degree or 15 degree, large angle grain boundary. No? So we could make, for fun, we could make that once. And I will put here, instead of 5 degree, I will put 15 degree. Okay, and plot that again. Now the left grain map will change. The right one will not be affected by it, but the left one will change in colors. Yes, it did. Now, as we have loosened the criterion, then now, of course, the grains become bigger. Yeah, because I only consider a grain when it has more than 15 degree. Before I accepted already more than 5 degree. So now all the grains have become bigger, and particularly this little problem which we had here, where was it? Here, in this grain here, has disappeared. There is no longer a green grain in here. No? But of course, instead of that, the grains have even become bigger. No? This grain here, now this blue grain here, is now, you can almost clearly say this is not true. No? It considers all this one here as one grain, although it's clearly this is recrystallized, this is recrystallized, this is not, this is not. But they have all grown out of that. No? This is probably a nucleus which has been deformed, formed inside of this blue area here. No? So good. How do we handle that? We need to go for a compromise. And I could show you as well what happens when we take 2 degree as a compromise. No, not as a compromise, as conditions. So we say. Exactly, yes, correct. We could now look in a moment how big is the misorientation. Now I took 2 degree, another extreme, and now you will see that this left grain will fall into many little grains. No? It will become, many smaller. The grain size, if you now say, let me plot grain sizes, then you will get completely different measures. Yeah? If you take this degree here, you will get small grain size. And if you take the other one, you will get a big grain size. So it's quite important to know that value properly. No? And unfortunately, there is no good recommendation to you, except you say, is this a true representation of what I see or is it not? No? So, for example, why is there no grain boundary between this and this one here? Because these 2 grains, it's clearly 2 grains. You see a clear grain boundary here, yeah? But the grain boundary happens to be, by chance, smaller than 15 degree. And that's why it is not plotted. Because these 2 grains nucleated out of the same mother grain, yeah? And they grew out together, they hit together, but by chance, yeah? And it can be 2 degree, it can be 0 degree, of course. No? So now, with my current situation, these 2 grains here are considered to be separate grains. And we had this other case here, this one here. Has it been separated? Yes, it has been. This is 1 grain, this is 1 grain. That was, so the 2 degree was obviously quite effective. Still, this one is still 1 grain. I think this 2 degree is good, except that we get now a lot of stupid spread little grains in there. Yeah. Okay, that I don't want. I don't want grains which are too small to be grains. So I hope you get already the power of this stupid software. Yeah. Why do I say stupid and power at the same time? Power means it's enormously powerful, but stupid means it requests you to make the right decision. Yeah? It does not tell you the grain boundaries are like that or so. No? You need to have material science knowledge in it to understand that. So let's make again, where is, properties down there. Here, grain size. Let's say I accept a grain only to be at least 15 pixels large. Let's see what happens now, what it will do now. To do these calculations, a few of them have dropped out. No? You see there's less colored things inside, but this one here obviously is it really a different orientation? No, it's not. That's the funny thing here. Yeah? I don't see anything in here, but obviously the software sees. Yeah? And just tell you the amazing amount of calculations which happen here using this 2 seconds waiting time. Yeah? For every pixel, it needs to look what are the misorientations of all the neighboring pixels. And to calculate misorientations, you need to consider all these 24 by 24 variants to consider what is the misorientation 0 or is the misorientation big. I mentioned it, the symmetry operation. This is fantastic calculations which are happening just in a split of a second. Yeah? Good. It's still not super satisfying. I still see some little disturbing features in there. So probably the 2 degree is also not the right selection. So let's go. I go a little bit bigger. But I will not find a proper setup. I will not be able to really separate into the right what I see by eye. That is probably not possible. I have started writing, or I wrote, software which includes more human knowledge. This is kind of stupid software. It just does simple calculations of misorientations and not considering anything else. But you can say, let me consider a grain to be something which is connected to the other pixels by certain rules. And these rules are not only misorientation, but there are more rules. For example, amount of dislocations inside or so. And then you can start writing your own code which modifies or which analyzes these maps much more powerful. And there is actually, in principle, you can export all these data and then start writing your own code. Yeah, it's fantastic. You use MTeX or you write your own basic crystallography tools. I had always fun with that. Let me go to some. No, here properties again. Properties. Now let's say I take a compromise value here and I compromise value here, and okay, let's calculate. Let's hope we get to something reasonable. And the rest we will throw away. Ah, yeah, it looks pretty good now. It's still, there are still some grains being created here, no? Which are actually, where is it? Actually not really a subgrain, not really a different grain, but perhaps we can live with that. Nah, I go to 5 degree. It seems to, the default seems to be, at least for a quick shot now, the default seems to be the best set. Yeah, but then it doesn't separate there. It can't help. It's impossible to do it perfectly satisfying. But you see how tricky that is. You can modify your grain size by selecting what you mean is a grain. No? And it is up to you really to make a proper selection there. Okay, now we are there. And we continue now. We say, okay, this is finished. This story, what do I call it, grain or not, is finished. What do I want to do now? I want to, and I delete that here. Delete. I want to now plot the internal misorientation. That's what I said, no? Before I came to the idea that I show you what is a grain. So I select a map, and this map will be called grain orientation spread. Yeah, let's take that and calculate. Now it's again an amazing amount of calculations going on in this very moment. And what is the funny coloring here? Why is it not considering all grains? I'm a little bit surprised. Where is that thing? Did I make a mistake? It is this one, yeah? Properties. Grain orientation spread. Yes. Let's take that off here. None. Okay. Huh? Why is that? Why is it not plotting all grains? I don't know yet. Have I made any restriction of my partition? No, I have not. Huh. Something is strange. Grain orientation spread, let me look. Is there any limitation? 0 to 100%. Okay. 20 degree. That's strange, honestly saying. Calculate again. Is it really right? Yeah. Orientation gradient, no, that's not. Why is it not coloring all grains? I don't understand that now. Let me see that again. Where was the IPF? ND here? Ah, so it's still there. Yeah, okay, good. There it is. What is that? Looks like a bug. I have to search for a moment. What could be wrong? 5, 10. Apply partition before calculation. Yes, everything good. Any problem? In principle, it should color all grains, but it seems not to color those grains which have very strong orientation gradients inside. And let's see, perhaps this limitation is set wrongly. So it goes currently up to 20 degree. Perhaps I need to go to 40 degree. Let's see. Here. Absolute 20. What happens if I go to 40? Okay. No, it's not changing. What is that funny thing? That's not supposed to be like that. Yeah, maybe the software has some internal selection. I'm quite surprised about that, but delete that again. This one we delete as well. Strange. Take that off. Grain orientation spread. Okay. Try it just once again to calculate it again, but I think this will not lead to anything better. No. Let's leave that software once. No. I don't know why this happened. Maybe I'm making a mistake which I do not yet. And there is 7. Okay, which I do not understand yet. Well, let's try it again. Okay, perhaps I have done some operation which dropped some data out. I'm not quite sure. Let's try the map again. Not image quality, but grain orientation spread. Let's cross fingers that this time it works. Oh, this is even less. What's kind of terrible? I have never seen that before. Really strange. Yeah, it shows only from 0.4 to 0.4 degree. It's very strange. Looks like a bug. Say what? Yeah, but it seems it does not want to calculate that. Let's try a different. Yeah, this is even the stick doesn't help now. Let's try grain average misorientation. What does this do? Calculate that one. Okay. This takes a longer while, yeah, as you see. But I believe it will calculate eventually. Otherwise, we have to try it with version 6. I would guess this is a bug inside of that software. I have given these presentations maybe earlier with version 6 and not with version 7. Okay. Let's hope it's doing something now. And otherwise, I have a a dry presentation of this same thing, but I would like to really do it with you here. This is also not calculating. Hello, hello. What's the time? Oh, that's not nice. No, that does not look as if it works. No. Let's try the other version of OIM, version 6. Perhaps it works with this, but I'm not sure whether I can load these data in there. Let's see. Yeah, it is. Let's try it again. So, and this is grain orientation spread, and okay. Nah, it's the same thing. Verdammt. I don't know what that is wrong. That's certainly a bug, but I don't know why this appears suddenly. Properties. This one here, poof. It doesn't do the right calculations. It's very strange. Which is a pity, because I really wanted to make this this exercise with you to guide you through that process. Then I need to, for the moment, to show you this particular example. I don't like it. I'm not happy about it, but I need to show you. Oh no, this is the wrong microstructure. Then I need to show you this as an example without calculations. That's not nice. Where is it? With the large overview, grain, misorientation, grain boundaries, pattern analysis. There should be something different. Where is it? No, you get me here. Data analysis. Yes. Okay. It is this example here, but I'm unhappy that I can't show it to you in live. It would be more interesting because we could get to many problems as you see it now. It usually works. I don't know, perhaps it's an installation on my computer. I'm sorry, but this one here, so I show you what it can do in principle when everything is working well. So you remember this is our microstructure, yeah. And I have now, and that's what I wanted to do with you. I wanted to calculate the orientation distribution of it, yeah. So, but I wanted to do this after I had worked on this separation. But okay, now we can't. We somehow have to do it with the finished calculations. So this is the Euler space of the whole sample here. That means the orientation distribution function of all grains here. And whoop, where is the pole figures? I don't show them? No, then I will show it later. Okay, so I can just show you there is a fiber here. There's one fiber of orientations here, which is called actually the alpha fiber. And I will explain you later what that means. That means there's a whole range of orientations which are all following this tube in orientation space. And there is a second tube in orientation space, and this tube actually starts here and then continues here, 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 here. So this is actually going out in this direction. Yeah? If you put these slides all on top of each other, you will see one tube here and one tube running here. And this one is called the alpha fiber and one is called the gamma fiber, but that's not so important. Now, let's do what I wanted to show you live, but I can't for some reason. I will check later during the break. So, I wanted to plot the orientation spread map. I don't know why it doesn't work, but it does not. What you clearly see here in this orientation spread map, there is these blue grains. These are the crystallized grains. They have virtually no change of orientation. That's why they are very low here, no? Almost 0 degree. And there is the other colored grains which have a strong misorientation. And once again, before you can do that, you must make sure that it has the right grain selection. Okay, now we say I want to accept for a filtering only the orientation spread which is smaller than 10% of the maximum. So I do that, and what is left over is only those grains which were here in dark blue. No? So all these grains are left over, and I plot them again as an IPF map. Good. Now I see, okay, this is already quite a nice separation of deformed grains and non-deformed grains, but there's obviously some deformed structures are also left over. No? And why is it like that? And here we come to this trouble. What does the software consider to be a grain? And these things here are obviously considered to be an individual grain because they have a misorientation to their neighbor bigger than 5 degrees, but still they are in principle not a separate grain. And they are small, and that's because they are small, the orientation spread is not very big, and therefore they are still selected in the wrong partition. So let's plot a grain size map, now only for these grains. And I find, okay, there are small grains plotted in blue and large grains in all other colors. So you can do this easily with the software. You can say, plot me the size of the grain in form of colors. You can also plot it in form of a distribution of sizes. And we do another filter. And this filter will call now grain size. The grains should be larger than a certain range. At least all these big grains I want to pick. So I let that filter. And now it looks like a proper filtering. All this little garbage here has been filtered out. There may be a little bit mistake. Some of the nuclei I will miss, but doesn't matter. Mostly I do a right analysis, and now I have actually a clear separation of the deformed structures and the non-deformed structures. Okay, and now I will plot the orientation distribution. I will calculate the texture again using this harmonic spherical spheric harmonics expansion calculations. And I find that the texture now looks very different. Yeah, and what you particularly see, this fiber here has disappeared, and only this fiber here, which sticks out in space here, is still there. So obviously all the recrystallized grains, they all follow only one fiber, the so-called gamma fiber, while all the deformed grains we will see follow mainly the alpha fiber. And we will see, oh yeah, and this is now important. Out of this texture, we are calculating the pole figures. And now you can apply nicely your knowledge about pole figures. Who wants to come to the board and explain us? No, I don't do that. But I explain you. I told you that all these grains we're looking on the 1, 1, 1 direction, yeah? Actually from the normal size. We are looking on all the grains show the 1, 1, 1 towards the normal direction. And that should point out in the normal pole figures, in the 1, 1, 1 pole figure, to be all grains pointing out to the center. And exactly that's what you see here, yeah? There is a strong peak of grains having a peak, having the same direction here to the center. And then there is a ring around that, and this ring is simply the grains are turning around that 1, 1, 1 grain. This 1, 1, 1, where's my soap piece? Over there? Yeah. So the grains, actually they are standing all like that with the 1, 1, 1 in normal direction, and they just rotate around that. So that makes this homogeneous ring. It's not fully homogeneous. We see actually that it has 3 maxima. And that means obviously there is a particular rotation of these 1, 1, 1 grains with the 3 maxima, which is also preferred. Yeah? It's not simply a completely homogeneous rotation, but there seems to be one set of these rotations a bit more preferred than the others. Now you could ask your question, is this enough grains to make sure that this is really true? It's probably not. No? So I would then go and make a second map and show and look at least one more map and look, are these peaks coming out again at that same place? If it comes out, then I start feeling this seems to be good. And there is, of course, one indication why it could be right, because one of these peaks is pointing exactly in in the rolling direction. And that could show that there is something about rolling, something about deformation, which makes these 1, corners tilting exactly parallel to it. Could be, but why is then there nothing on the opposite side? Yeah? You would wonder, huh? The grain doesn't know has it been rolled forward or backward. So in principle, if there's a pole here, there should be a pole here. And if there would be a pole here, then there would be automatically 2 poles here. So I believe this is not really this is indicating that this is not enough grains. And I would go and measure at least one more map at a different corner of the total sample and look, does it come out the same? No? And okay. And but the principal thing, what we see is this 1, corner standing of the grains. And then we see, okay, for the, this also makes a ring, and this also makes a ring. Huh? Is that possible? The 111s make a ring and the 001s make also a ring? How can that be? Yeah, of course it must be. Because if I fix my sample on the 111s and turn around, then also the normal directions from the 001s make a circle, yeah? Of course. So the 001s, the diameter of the 001s is different. The difference between between the 001 plane and the 111 plane is 34 degree. That means the diameter here must be 34 degree different. Huh? It's a circle with 34 degree difference to that one here. And like that, there is clear crystallography behind here. And also here, this ring here is of course also due to a rotation around that peak here. Huh? Mm-hmm. Okay, and now let's continue and say, okay, now we filter. We want to see how do the deformed grains behave. So we take another filter, we say not this partition, so all the others. And as a result, we get now a microstructure with holes. And it contains only the deformed grains. And it gives us quite good confidence, actually, that this is really deformed grains. There's a little bit of debris. This grain here, for example, has obviously wrongly been defined. This one here as well, but we can tolerate a few grains. No? Now, can we really? This grain here also, this grain here also. I could go by hand and could say I kick them out as well because I want more accurate data. This one seems also to be not good. Why has it been included? Because there was no 5-degree misorientation boundary, so it was considered to be belonging to this one here. No? So then you have to, as a smart person, say this is not right. This is recrystallized. I don't want it in. I kick it out. Same thing with this. It has only 5-degree boundary here. That was it included. This big one here is also not making fun to us. No? This needs to be also kicked out. Probably it has a very small misorientation here. Yeah? That's why it was considered by the software to belong to the deformed structure. And it messes up our calculations. It really does. If we would now have the live version of it, I don't know why it's not running, then we could simply say this grain also not. Yeah? It's very simple. You just click in this grain and say, throw it out of the partition. Beautiful power. Okay. So, but anyway, if we have now this selection made, we can plot again the ODF. And you see the ODF between the recrystallized grains and the deformed grains is really completely different. Yeah? While you have in the recrystallized grains only this fiber here coming up here, in the deformed grains you have mainly this fiber coming up. But not only, this fiber is also there. You see it, yeah? And that means, and we remember this fiber was 001 parallel to ND, so these are the red grains, and this fiber here is 111 parallel to ND. In the deformed structure we have both. And indeed we have the blue ones deformed and the red ones deformed. The blue ones make this fiber here, and I really need to come back to the computer to show you this, and the red ones make this fiber here. And yeah, you may ask, how do I know? How do I know that the red ones are belonging to this one? You can now click into the microstructure, and I'll try again, and then you will see that only these grains, only these areas are lighting up. Yeah, and then you click into the blue ones and you will see only these grains are lighting up. Oh, let's try that. But let's look again into our pole figures. So this is not yet refreshed. I was wondering, why are these pole figures not showing what I want? I need to refresh it, of course, yeah. So this was deformed grains with these funny circular fiber, and this one is now the that was the recrystallized, and this is the deformed grains. And this time it's more difficult to read, yeah, because we are seeing at least two overlapping fibers, no? Or two overlapping fractions of grains. One, these red ones, and one is these blue ones. The blue ones we understood already. They have a center pole here and a rotation around. We see this rotation barely, and there is still the rotation here, and there should be still the rotation here. It is there, but we don't see it so clearly because it's overlapping with another thing. So this was 111 parallel to ND. And then there is a second fiber, which is red, which is 100 parallel to ND. And that 100 is this one here, or 01. And that's a fiber here. And there should be a circle around that fiber here as well. So that's actually, here is a fiber circle. And yes, that's, is that actually correct? I'm a little bit surprised. Should not be like that. Yeah, it's not a full circle. All right, we see actually, it's a bit more complicated than what I tell you, but let's stay for the moment with this 111, yeah? And now let's, indeed, is there something more coming? No, it's not coming. Indeed, I need to look. So there's the 001, that's for certain, and the 001 rotates around, but we need to look which 001s are there. They are not rotating around 001. They are not doing a rotation. They are doing a different thing. And let's see whether I can get that software again running. I would really like to, oops, there it is still running. Grain spread doesn't work. Let's delete that one. But let's go and calculate again these pole figures, discrete pole figures. This one and 111. Okay, and soon we will stop with the exercises here. I hope it's working now and not, yeah, this is working. I don't know why that other thing did not. Again, do the layout changing to 1, okay. And plot the IQ. No, plot the inverse pole figure ND, yes, it's better. So, now I said I'm myself a little bit puzzled. It's also long ago that I really worked with this microstructures here. I said there is an 001 fiber which corresponds to these red grains. But now let's see if I plot all these grains which are corresponding to this one, which grains are there, which grains are colored here. So let me take all the grains which are red in this picture. They should be 001 parallel to the ND direction. And I will select them all, show highlighting, and show, I give them a different coloring again. Let's say yellow is quite reasonable, reverse, okay. And I will this time not click in here, but I will click in here to select those grains which have one direction into 101 direction parallel to ND. So let me click, do I show the highlighting? Yes, I do. And do I have here the right selection? Yes. Okay, so let's, oh, that was a wrong click. Clean up. Okay, click here into the center. No, it should show it here as well. Why doesn't it do it? Show highlighting. Okay, good. Yes. So it doesn't color all the grains which were red because some of them are more pinkish, but it covers quite a lot. And what we see here is actually, it seems that there is a, okay, this grain here was, these grains were marked which have one direction here, but it seems that there is not a very clear selection. There's also grains here and here which are, so it's spreading out a little bit here in this direction, yeah? So let's look what happens if we plot that as well. I click here as well, yeah, for selection, right? Okay, now the other half of the pinky grains is coming, and I click here for selection. Okay, and now probably all the other pink grains disappear, yes, and only the blue ones are left over, no? So, and what you see now is these red grains which I marked, which by eye appeared to me doing a rotation as it is here around that circle. There's actually a little bit a different rotation. It's not really circulating around that pole here and then making this round here, because actually this is not colored. What is rather happening is I'm spreading out around this axis here, yeah? So I have obviously a rotation about RD. So if I rotate about this one here, I take this grain, I rotate about this, then I come to this spread here. And then I come actually also here, I do the RD, I see this spread here and this spread. Let me try to show that again. I have a grain standing like that, and I start rotating it like that. Then I get this spread here, and this spread here, so like that, yeah? However, when I'm rotating like that, I should have rather a spread like that. So there seems to be something different. It's not a rotation about, so that was clear, this was a rotation about ND. Here, this point makes a circle here. But these grains, the grains which are reddish and pinkish, these make a rotation about this direction here. So there is actually two different fibers. One fiber rotates about ND, and actually 111 around ND, and one rotates about RD, but actually 001 about RD. So this is a relatively complex texture, but you see it actually separates then into non-deformed, into deformed and non-deformed grains, into deformed and recrystallized grains, and you see the deformed grains split themselves up into one fiber like that and one fiber like that. And okay, this is, of course, nowadays this is a solved problem, how these textures, recrystallization textures of IF steels form, but you hopefully see and can follow how powerful the software is in order to allow us to explore that texture, no? These texture problems. And I don't know whether you have questions to that, or whether you understood at all in general. Is it all clear enough?
If there's a second phase,
yes.
the size is also bigger.
We will come to second
Define the grains.
Indeed, this is all single phase, of course, no? And I will show this afternoon, I will show an example where we have BCC and FCC, both phases available, yeah? And then we can get completely new things, no? And we will see then the orientation relationship between austenite and ferrite, and plot that in details. So I think if you are happy with this, I have not done any texture calculations so far, but I have shown this in theory, no? And you just hit the button for texture. Maybe one example shortly to finish that. If you want to calculate the texture, then you say new texture, and now comes up all things which you have learned from me, or you haven't, but you have at least heard from me. And that is, first you have the selection of harmonic series expansion, and you say, yes, this is what I want. Edit this. You see, I can select the rank, expansion rank, yeah, 16 is default. If you have a sharp texture, you go to higher. If you have a soft texture, you go to lower. And yeah. In HKL it is also available, but it's somehow hidden somehow. I don't know exactly where it is hidden, but it is there. It's a very important parameter for texture. You must have it. I don't know where it is in the HKL software, but it is there. And then the Gaussian half widths for how do you spread out your individual peaks. And then what I have nerved you, so where I was a pain in your neck, sample symmetry. No? You can actually enforce sample symmetry. If you say, oh, my pole figures, my measured pole figures are sufficiently symmetric, then so they show an orthotropic sample symmetry, then you can say, okay, I want to calculate as if it is perfectly symmetric. And then it will calculate a texture which has orthotropic sample symmetry, and you will see then it's perfectly symmetric because the program enforces symmetry to that. No? If you use triclinic, then it will not have sample symmetry, and you can also have an axial symmetry, then it will rotate it all around there. No? Okay, so but let's keep with triclinic, and yes, say use all measurement points in statistics, then it calculates a little longer. But you can say also use also only 1,000 points, then it's ready in a split of a second. But let's, for the moment, try it once with all. Okay, we calculate that. So we selected this calculation scheme, and now we need to define what we want to see after these calculations. So we want to see a pole figure, for example, an 001 pole figure. We want to see an inverse pole figure, for example, that one where we show the ND direction. And we want to see an ODF. Yeah, let's just keep the standard here. Okay. Oh, you could also calculate the fibers. That means the intensity along these rotations which I have shown you. No? The 111 rotating along ND, or the 100 rotating about RD. I think we could speak just about this example for the next 3 days until you have absorbed all the possibilities. But I just do it now for this further few minutes. I calculate, and now you see, oh, it goes on. The higher is the extension rank, L equal 8, the longer it calculates, because the more C coefficients it has to find. Yeah. If we go to 16, what did I say? No, 22 was it? No, 16. Then it needs 700 calculations already. No? And it goes slower and slower. And if you are, if your boss is an impatient person, then he doesn't want to wait until you have come all with all these calculations. And we are only at 12, and we want still to go until 16, and it goes slower and slower. Yeah? Therefore, it is then sometimes a question of either selecting only random points or selecting actually a lower expansion rank. But of course, you should not sacrifice accuracy for speed. No? So better you finish in 10 years your PhD thesis than it's wrong, yeah, or not. Okay. No, let's give this the weight. $15, and soon we will be through. So the amount of calculations is quite dramatic, which happen here inside. No? Mm-hmm. It doesn't look like that, but it's actually quite a demanding situation. What you can also do, maybe while this is calculating, just think a quicker way is so-called discrete binning. In this case, the software does the following. It makes little bins, that means little areas of equal size, and it just calculates how many points are in these areas. It doesn't calculate a function, but it just calculates a distribution of densities. So at the end, it can also display densities, but it has not internally calculated all the harmonic series. No? It depends on what you want to do. Sometimes these C coefficients can be quite powerful. I'm not going to talk about that. Good, but we're coming to something. 16 is, nothing will happen after these calculations. It has calculated all C coefficients. Now it just calculates the function. And I warn you, okay. Yeah. And here we go. And now it will calculate, I think, also the pole figures. But this is so quick that you don't see. And then you can go and say, okay, plot what you have done. New texture plot. And we say just, I want to see the pole figure. Okay, hop. Oh, there it is. Yeah, beautiful. And we put that down, and we put that up, and we clean up so that we see a bit better. Is it cleaning up? Yes. So, okay. Now this is the calculation. That is the density. This is the density distribution of this picture here. And interestingly, from this picture you would have said, okay, I think the rolling symmetry is clearly observed. No? I clearly see that there is a mirror plane here and a mirror plane here. So it looks as if I have measured enough data to really represent a nicely symmetric texture, which for me this would be a sign I have measured enough. But if you calculate, then you see actually that the density here is not as high as the density here. No? So it's not symmetric. It's getting approximately symmetric, but it's not yet purely symmetric. And that shows probably in the map which we have seen, it's not enough grains. Obviously there's a part of the texture is missing. Probably you would go to another place of the sheet, you would find here more pixels of this orientation here. No? So you can see from this that this is most probably not enough measurement to be really representative of the texture. If you need an accurate texture, then I would not allow you to take that. I would say go back, make another measurement at a different place, and let's see whether this comes out the same. I don't believe it. No? But okay, that's how it is. And of course, this is the normal pole figure. And now we can also plot the inverse pole figure, texture plot. Where is it? Pole figure, inverse pole figure. Okay, let's plot that as well. And that is this one here. And now you can, it's so beautiful. This is really a fantastic example. Because what you see here now, oh, there's one big blob. Yeah. And what do I plot here actually? What is this inverse pole figure? I'm plotting the direction of the Z coordinate, sample coordinate, in crystal coordinates. Yeah? So this is the crystal coordinate system, and I'm plotting the direction of this direction here. And what do I find? Obviously all grains have the normal direction parallel to a 1-1-1 plane. Yeah? And that's what we figured out already before. Yeah? I told you there's a 1-1-1 fiber, 1-1-1 parallel to ND. I see it here. And okay, there seems to be also a weak 001 fiber parallel to ND. But now let's look. I promised you there is a second fiber. This one is called the gamma fiber. 1-1-1 grains, 1-1-1 crystals pointing in the direction of the normal direction of the sample. And I promised you there is a second fiber, and we just need to calculate it quickly. New properties. I just need to calculate this second inverse pole figure, and that is actually the rolling direction. Up. 0 here. Okay, up. This is very quick. We don't need to wait for that long. There it is already. And we can now plot it. Inverse pole figure. This one here. Okay. Oh, it puts it together. So I didn't want to. Oh yeah, well, now I deleted it. Stupid. This one here. This one off. Remove. Okay. Calculate. Okay. Aha. This is actually something which I told you wrongly, of course, yeah. Slowly it comes all back. I have really long time not worked on it. It's a shame. I told you a little bit wrong things, but it doesn't matter. I told you the principles, and you still follow me. And if we would work face to face, just two of us, then I think I could be a bit more focused what we really see. But what we see now from plotting this pole figure, which is now indicating which crystals run in RD rotation, then we see, there is also a fiber, obviously. No? And this fiber, what does it mean? Actually, that the 011 crystal directions point into our fiber direction, into the 100 direction. And we have not yet seen this in all my plots which I have done. We have not clearly seen that this is the fiber. But the inverse pole figures, they show you clearly that there is a correlation between the direction of a sample and the direction of a crystal. Yeah. So I know this is not so evident to every one of you now. You need to probably play with the software and get a little bit familiar with it. But we have the camera and me speaking. Probably with this you get an idea how to start with that. Yeah. And if you have a question, particularly in this case, we could also work on it together and I could explain it a bit more. But like that, maybe we keep it like that. We have two fibers in this material. One is 001 parallel to, so one is the normal direction parallel to the 111 crystal direction, and one is the rolling direction parallel to the 011 crystal direction. And yeah, that's it for the moment. Yeah, time for lunch. All right? Good? No complaints? I hope not. Yeah. I would not accept complaints, only praisals. Oh. Good, good. No. Say?
Any questions? You want to check them?
Questions to them? Ah, okay. Whom do I pick? No. I won't. Good. No, I'm finished. Yeah, for now. And later on we'll continue.